So now that we've talked about the pros and cons of synchrony, let's talk about the pros and cons of asynchrony. And this, of course, is going to motivate completable futures because they are an asynchronous way of doing things. But, of course, they have pros and cons like anything else. So recall what asynchrony means. It's a means or a mechanism of concurrent programming where the caller does not block waiting for the callee to complete. And a great example of this is dropping a letter in the postbox. You're probably going to be considered rather obsessive compulsive if you drop the letter in the postbox and then wait there for the letter the reply to come back. If for no other reason, it probably won't be delivered back to the postbox. It'll be delivered to your postbox, not the mail drop. So unlike, say, a phone call, right? A phone call, you make a phone call. If the person answers the phone, you have a synchronous communication. But texting and emails and mail are asynchronous. So what happens in asynchrony is that the async call returns immediately with something called a future, and then the computation that you initiated will go and run in the background concurrently. So the idea is you start something out, you get a result, and then you'll wait for the result to complete. But you won't block, typically, unless you're using older school concurrency and asynchrony mechanisms in Java, which we discourage you from doing. So basically, the processing takes place in the background independent of the calling thread's flow of control. And you can kind of think about this if you do pickup orders at a store, right? So during the pandemic, nobody wanted to go sit in a restaurant because they were worried about getting the virus. And so instead, they would place an order, and then they would go and they would have curbside pickup or whatever. And the idea was you would place the order, you would then do whatever you wanted, and then at some point you would drive to the location and pick it up, and they would make your order independently of you being there. So the whole thing was done in a very asynchronous way. And we'll talk more about the fast food model of asynchrony later, because it's got a great analogy here. When the asynchronously running computation completes, the future to it is triggered. So basically what happens here is that you initiate a call, you get back a future, the call runs in the background asynchronously, and then when it's finished, then the client can obtain the result of the call. And we'll say there's a whole bunch of different ways to have that happen. But that's the idea. The future doesn't really have anything valid in terms of a result until the asynchronous computation is done. And in particular, the client may or may not block waiting the results. It depends on various factors. It depends on whether the client has better things to do, like waiting for other requests to come from a user, including the cancellation request to stop that asynchronous computation. Or maybe it doesn't have anything better to do, in which case it'll start things running and then just wait for the response. Not necessarily the best way to do things, but it's possible to do it that way. A good example of asynchrony that was popular until recently when they deprecated it, but it's still a good example, is Android's async task framework. And the async task framework was used to perform background operations in background threads on your Android device, and then have the results published in the user interface thread without having to explicitly create threads or interact with threads yourself. So this was all done magically through a very cool pattern, which is basically the template method pattern on steroids. And so here's kind of how it worked. You could make something that was an async task, and you could execute a job on it. You could execute the async task, and that would go ahead and run computations on one or more background threads. And the background threads could block. Nothing wrong with having background threads block. So they could be doing things like downloading an image or downloading a video or doing some kind of database operation that would take a long time, like a big query and so on. But the user interface threads don't block. And the cool thing about the async task framework was the user interface thread, which doesn't block, could be called back to get information about either the success or failure of the computation, or you could also get back periodic progress updates. For example, if you were downloading a large file, you might have a status update that would show you how far along you were to get your computations done. And the async task shields client code from the details of programming with asynchronous mechanisms. It looks synchronous to you, but it's actually running asynchronously in the background. So let's talk a bit about the pros of asynchrony. One is you can make things responsive because the calling thread doesn't block waiting for the asynchronous request to complete. It's therefore available to do other work, which is good. You can also make things more elastic because multiple requests can be mapped to the underlying processor cores. And as you get more work, if you've got more cores, you just sort of auto-scale very nicely and elastically. Another nice thing about using asynchronous approaches is it often, if it's done well, and it usually is, it'll better leverage the parallelism that's available in modern multi-core systems. And you'll see this if you take a look at some of the examples like the search stream gang example. You'll see that the completable futures version often runs very well, and that's because it has a lighter weight way of being able to leverage the underlying processor cores because it doesn't block. Elasticity is particularly useful to auto-scale computations in cloud environments. As I mentioned before, completable futures are not themselves working in clouds, but you could use them in the individual portions of machines in a cloud environment. And of course, there are downsides with asynchrony. And one of the downsides is unpredictability. Even though you're trying to keep the response times low, because things are running in different orders and you have little or no control over the order in which things run intentionally, you may not necessarily know what order things are going to complete in. Now, this is a general problem with concurrency and parallelism, not just asynchrony, but it's exacerbated here because you're intentionally not caring what order things run in. And in particular, the results may come back to you in a different order than the calls were made. And sometimes that's good and you don't care. Other times it's bad and you want things processed in the right order. So additional time and effort may be needed if you want to reorder things in the encounter order as opposed to the completion order. Probably the biggest complaint about asynchrony is it increases the complexity of programming and debugging. And there are several reasons for that. One of the reasons, of course, is when everything is running concurrently in the background, then setting breakpoints is tricky. Setting breakpoints on one thread may cause the behavior to diverge in terms of what would happen if you weren't running in the debugger. So you may get different timing behaviors, you may get different ordering behaviors. It may just be complicated to understand. And of course, this all kind of boils down to the fact that the patterns and best practices of asynchronous programming are not necessarily as well understood because we haven't had as much experience with it. Once you get experience with it, it's really not that complicated, but with anything, there's a learning curve. Another problem is if you try to do asynchronous programming without the proper abstractions, you get what is commonly referred to in a loving way as callback hell. And this is a common problem with versions of JavaScript that have a very lame model of asynchronous programming. And so you could basically end up with these crazy nested callback-like models, which are next to impossible to program, next to impossible to maintain, next to impossible to debug. So the good news, of course, is that Java doesn't do this. Java has a much better way of doing this with modern completable futures. And errors can be hard to track down because things are occurring in different orders and so on. Again, non-determinism is a general problem with concurrent programs, not just with asynchronous programs. So whenever we talk about anything having to do with concurrency and parallelism and asynchrony and so on, that's going to be an issue. It's usually just a matter of learning curve. So let's weigh the pros and cons of asynchrony to see whether it's worth it. In order to decide to master the learning curve in asynchronous programming, two things really need to be necessary in order for the pros to outweigh the cons. The first of which is there's got to be a payoff for all this extra work. If you're going to go to the trouble of writing an asynchronous program, you really would hope that you'll get better performance as a consequence. And that indeed is often the case. So here we can see the results from that image stream gang example we looked at recently in class, where I explained how the completable futures did better than the parallel streams because it was a lighter weight way of handling multi-core programming and processing. So that's one thing you often see, not always, but you often see that works better. And of course, remember, we also talked about the fact that the image stream gang example was I/O bound, whereas some of the earlier things we looked at, like the search stream gang example, was compute bound. And so for I/O bound operations in particular, you can see that completable futures often give you a bigger win because there's less blocking going on. And another thing that's important is that the asynchronous programming model that you choose, whatever one it might be it a JavaScript model or an early Java Futures model in classic Java, or a more modern Completable Futures model in modern Java, or the reactive streams models, et cetera, it would really be good if it reflected as many of the key principles of the reactive paradigm as possible. And in particular, you need to ask that question. So Java's Completable Futures framework is nice because it gives you asynchronous programming that performs well and supports the reactive paradigm. And one of the really cool things it does is it makes asynchronous programming look very similar to synchronous programming by using the fluent interface style, where you can chain together these dependent actions. And that's nice. You don't have to do all kinds of crazy things with callbacks, for example. However, I would be remiss at this point if I didn't mention that there are other frameworks, in particular reactive streams frameworks, that are even better suited to supporting the reactive programming paradigm. And those include RxJava, which is this funny little thing that looks like an eel, I guess. I'm not quite sure what it is. And then there's Project Reactor. We're going to talk about both of those later in the course. They are intentionally designed to be supporting the reactive programming paradigm. Completable Future supports it, but not quite as effectively as these two frameworks do. But that's OK, because it's important to understand all these different models. So that's the end of the discussion of the pros and cons of asynchrony.